Yeah, so Brian Miner is going to kick us off here, and his presentation is titled "The Role of Production Engineering: What do we do and why it matters." Now, Brian, he's actually the founder of Evolution Well Performance, which creates digital content and offers practical training courses focusing on improving wellbore performance. And prior to founding EWT, Brian worked at various unconventional reservoir systems as a production engineer for BP and then later Chesapeake Energy. Brian holds a Bachelor of Science in Chemical Engineering and a Master of Science in Natural Gas Engineering and Management from the University of Oklahoma. Now, when Brian's not obsessing over coffee or pouring through petroleum technical literature, he really loves to spend time playing rugby, working on his culinary efforts. And if I could share the picture, he really likes to imitate Chris Hemsworth as Thor, and he's does a pretty good job of it too. So, Brian, why don't you take it away?
A bit more about my background, as Graham mentions. I'm the founder of Evolution Well Performance, and for my career, I've really spent all of it in production engineering, focused on optimizing wellbore performance in unconventional systems, everything from stripper wells and gas condensate fields, which require every form of artificial lift you could imagine, to high pressure, high temperature gas wells where deliverability really isn't an issue and you don't require any form of artificial lift. So it's really about choke management till the wells die, essentially. And so that's a little bit about my background. And okay, so I already gave you all a little bit of my background, and my role for today is really primarily going to be to set the table for RTA in production engineering and how it can be used and benefit us. And so most of mine will be painting the picture of what the role of the production engineer is, and I'm going to do that in very broad strokes and then free up time for some of the more technical dives a little bit later in the day. And then next week I'll present my own case studies for why production engineers should be using RTA and what it can do for us. So to begin, I wanted to pull back a little bit and take a look at a flow chart that we're all pretty familiar with, and it's essentially the phases of a field development plan in exploration and production. And it consists of exploration, appraisal, development, production, and abandonment. But we can draw an analogous flow chart for the individual well level that might look like this: planning, drilling, completion, production, and abandonment. But what these flowcharts fail to emphasize the relative importance of the production phase itself. And primarily, there are two key perspectives that I'm talking about when I'm talking about this relative importance. And the first one is time. So when we consider the relative time scales of each of these phases, we would probably redraw the flowchart to look like this. The planning, drilling, and completion phase may take a couple of years at most. You wouldn't expect that much beyond 5 years at the most, I would say. But the production phase itself is often decades, especially when you start talking about field scale production efforts. And then finally, the abandonment phase. And so this is really where we start to understand the importance of the production engineer to the holistic E&P world. We spend all of this money to put a well in the ground, and then we have a very long production phase at which the production engineer is responsible for managing that. And that kind of leads us to the second key perspective, and that's an economic one. So for all of the phases, we generally have to invest capital with the exception of the production phase. That's the only phase out of these where we're actually generating a revenue stream that's going to ultimately result in a return to our company and our shareholders. And that's really what we're after at the end of the day. So one way to view the production engineering world is to view us as stewards of that initial capital investment. And what our role is to optimize the production phase to ensure that we can actually deliver that return. And these two perspectives of time scale and economics are what I want to kind of pivot from to discuss the differences between the production engineering role and the reservoir engineering role, because I know that we have a good mix of both production and reservoir engineers on the line. And I think it's important to point out the key differences, or some of them, because we often use the same tools, but we use them in different ways. And so when we think about the objectives of the reservoir engineer and the production engineer, it might look something like this. Typically, your reservoir engineer is looking at much longer time scales. So they're interested in what is the cumulative production from this well? What, and by necessity, what is the ultimate long-term value that that well is going to deliver, or that program of wells will deliver to the company? And so one of the tools they use to do this is they forecast using typically some DCA method to understand what are the ultimate reserves for the well. And their optimization responsibility, or their key area of interest for optimization, is going to be tied to reservoir deliverability. The production engineer, on the other hand, we're typically looking at things on a much smaller time scale. So it can be as small as hours when we're really trying to diagnose something, but typically it's days, months, or sometimes years when we're looking at longer term trends. We also typically use decline curve analysis to forecast performance, but it's more so for understanding the key performance indicators of the well, or identifying well fall off and giving us a clue as to when we need to investigate wellbore performance with an intervention or a slickline dip in, something of that nature. And so because we have these much kind of tighter, smaller timescales that we're interested in, we're much more focused on optimizing near-term value or cash flow, these periodic cash flows month over month that will ultimately result in delivering that ultimate net present value of the well that the reservoir engineer is interested in. So we can already kind of see how these roles are different but linked. And obviously the production engineer is primarily focused on optimization of wellbore deliverability. And so from there, I'll dive a little bit more specifically into the role of production engineering. And I found this quote from my favorite production text, which is by Economides. And it says that production engineering is that part of petroleum engineering that attempts to maximize production in a cost-effective manner. And I really like this quote because it captures this kind of dual forces of production engineering that we're always struggling with, which is primarily maximizing production, but there's typically a cost associated with that. And so how much can we spend and how much will that improve production? And if we take a typical example here of just a declining gas well, that's going to generate some amount of revenue, but we're also going to be spending some amount of operating expense to generate it or to keep the well flowing. And the difference between these two is what I term lifting margin. And it's essentially the runway that we have as production engineers to manage that decline curve and continue producing revenue. And in an ideal case, maybe you could keep that OpEx flat, but as most of the production engineers know that are watching, typically later in the life, as the well loses rate and pressure, is when we start to have all our issues, whether it's loading, scale formation, anything of that nature. And our runway at that point is much smaller. So optimization becomes critical when you have much less leeway. And that's really where the role of the production engineer is most aptly demonstrated. Is these lifting costs tend to actually increase over time, and based on our efforts to optimize the wellbore, we can either extend that economic runway and deliver the NPV that we promised our shareholders, or we can, if we do things poorly and don't optimize the well, we can significantly reduce the runway. And so that covers both sides of the coin of production engineering, and is a good segue to jump into some of the more technical side of what we do And for that, I will show the unconventional production system. And there's a lot going on here, but I think it's important to show because it demonstrates the link between reservoir and wellbore, or those two disciplines. We sometimes think about them in silos, with reservoir optimization being different from wellbore optimization, but really to be effective as production or reservoir engineers or petroleum engineers, we need to think about them together, and we need to collaborate. And there seems to be a running theme with these SAGA webinars of incorporating an analogy. And so I'll try to throw one out here. I think about the roles of the reservoir and the production engineer as taking a road trip. And the reservoir engineer is generally concerned with the destination, but the production engineer is driving the car. And if you're trying to go to Portland and you're not communicating, the reservoir engineer might think we're going to Portland, Oregon, but the production engineer might take you to Portland, Maine. And so it's really important to understand and communicate what's happening between the production and the reservoir roles. But back to the production system, it's really, we always get caught up in thinking about rates and what are we producing at surface and what's the value. But mostly we're really focused from a technical perspective on controlling pressure losses and understanding pressure losses. And the first one is the losses that you see within the reservoir itself, followed by losses within the completion. And this is generally the realm of RTA historically, and where all of the power comes from, is characterizing the completion and the reservoir performance. And it's generally at this point where you've described the inflow or reservoir deliverability to the wellbore, and we're handing over kind of the flowing capability of the well to production engineer. And then from that point, we obviously have our outflow well deliverability and pressure losses associated with that, which are primarily the potential energy of the fluids and frictional losses. We have choke losses sometimes. If you have a high deliverability system with a lot of pressure, you can have a choke management system which controls reservoir deliverability. And then finally, we have some pressure losses in the facility. These tend to not be as important, and sometimes the production engineer is responsible for them, but typically they aren't, and that might be a facility engineer role. But we can see from the technical perspective now that this entire system is linked. So the disciplines need to be linked as well. And it's our job as production engineers to optimize the wellbore or outflow deliverability by minimizing any pressure losses in the system that can. And so another way to show that or demonstrate is simply a nodal analysis view, where each of those systems, the facilities, choke, wellbore, and reservoir, is a component, and the pressure at each point downstream or upstream is a node. And these pressure losses are described generally by a relationship between the resistance, which is some combination of fluid and rock properties in the diffusivity equation, for example, or a multi-phase flow correlation from the mechanical energy equation. So the goal here of the production engineer is to minimize those losses, and oftentimes we only have measurements of pressure at the wellhead, and we're relying on estimating bottom hole pressure. And the reservoir engineer really needs a good understanding of bottom hole pressure and able to solve the deliverability from the reservoir or solutions to the diffusivity equation. And that begins to kind of show from a technical perspective why it's important for the production engineer to understand RTA. It's because what happens at one end of this system is not independent from what happens at another end. And so the production engineer has an influence on analysis that the reservoir engineer is performing, And the deliverability from the reservoir can dictate what we do on the production side in terms of when we install artificial lift or downsized tubing or whatever we might be doing. And this is something that I'll be exploring in more detail with some specific cases, practical use cases next week. But I did want to introduce it as a mechanism just for linking our two roles in trying to bridge the gap and answer the question of why we should care about this as production engineers. And for anyone who's not a production engineer in the room, some of the sources of pressure loss that we often are fighting on the production side is scale. We might have hydrate formations, the bottom left there, erosion or plugging of the choke, corrosion of the casing or tubing. And if anyone caught the JPT issue a few issues back, they show this gummy bears in shale production. We're always producing some unknown foreign substance that we're having to deal with. It's either plugging the chokes or plugging the lateral or the tubing, and we're trying to characterize that and eliminate it. And so for final thoughts, generally, as I wrap up, what I want people to take away, we probably have managers on the line who are wondering, why should I care? Why should I keep watching the webinar? And the production engineers, same thing. What is the value of this to me? And it all has to do with optimization of our wellbore. And what RTA and the reservoir models that come from it can enable us to do is not only understand the inflow and outflow intersection points, our operating points, but it allows us to do that through time and under different scenarios. So we can begin to run all of the sensitivities of when should we install tubing, what size tubing should we install, if we install X artificial lift and we get a reduction in bottom hole pressure, what uplift do we expect? What's the economic value of that? How much did it cost to install? And we can truly optimize our wellbore over the life of the well, and having that power at our fingertips as production engineers enables us to deliver or maximize all of those periodic cash flows and ultimately generate the maximum return to the company and to our shareholders. And with that, that's kind of my spiel for why this matters and why we should be more engaged with reservoir and, if not directly, using RTA techniques as production engineers.
Thanks a lot, Brian.
Yeah.
I'm just going to give a reminder to the audience that we do look forward to any questions that you want to submit. If you look around the Zoom pane, there should be a Q&A box. So any questions about Brian's talk or any other talks you hear today, just feel free to submit them and we'll answer them. I've got one question for you, Brian. So when we look at the life cycle of a well, and specifically the different phases of artificial lift through that life of the well, I wanted your opinion about, currently in the industry, how much of this planning is done using, wellbore and reservoir modeling versus experience? What do you think about that?
Wow, that's a great question. In my experience, there's a lot of both, but they're not always done at the same time. So if you have a very well-developed field, you often, as a production engineer, know when your wells are going to liquid load. You know when you need to be installing tubing. But what you may not know, you may, or at least you think you know, but these reservoir models will allow you to actually fact check yourself and say, could I have optimized it that little bit more? And so I think that they're both being done, but it's not always collaborative. And from my experience, the production engineering on our side, we're typically not using these RTA workflows to drive artificial lift optimization at all. It's mostly experience and third-party vendor software around a specific type of artificial lift.
Got it. Thank you for that. Yeah, I hope the technology in the industry can keep advancing, so it's more convenient and practical to do it, from a modeling perspective. So I think with that, Brian, maybe we'll let you stop sharing your screen and we'll move on to the next topic. So our next presenter is Dr. Jem Sarica, and he's a FH Mick Morelli / Cimarex engineering professor at the Petroleum Engineering at the University of Tulsa. So he's currently serving as the director on 3 industry-supported consortia at TU, and this is on fluid flow, paraffin deposition, and horizontal well artificial lift projects. So Jem's research interests are production engineering, multi-phase flow in pipes, flow assurance, and horizontal wells. He holds a Bachelor of Science and Master of Science degree in petroleum engineering from the Istanbul Technical University and a PhD degree in petroleum engineering from TU. Jem has previously served as in various SBE committees, and he currently is a serving member of the SBE Production and Facilities Advisory Committee. He was a member of the SBE Journal Edition Board between 1999 and 2007, and he has served as an associate editor of JERT and ASME between 1998 and 2003. He's a member of the Technical Advisor Committee of British Hydrodynamic Reservoir Group Multiphase Production Conferences, and he served as the Technical Program Chair of BHRG between 2008 and 2012 conferences. More recently, Jem is the recipient of the 2010 SP International Production and Operators Award, and even more recently, he was recognized as a distinguished member of the SBE in 2012. And so with that, Jem, do you want to take it away and let's hear about your talk?
Thank you for attending this webinar. I think Brian's talk was a good segue for my talk. He already showed and justified why wellbore matters, and I will a little bit go more into detail of that and talk about multi-phase flow dynamics in unconventional wells. Why do we want to do that? Brian alluded to that a little bit. Ultimately, what we want, measure things at the surface and estimate the bottom hole conditions. Primarily, we are interested in bottom hole flowing pressure, and that will help us to know reservoir performance, inflow performance. However, there are challenges to go from wellhead to bottom hole. I will try to address some of those. Along the way, I will talk about what it means for fluids to flow in wellbore. If you look at it at a high level, I like to first classify wells based on produced fluids, and then based on flow descriptions, primarily flow patterns. And then I will talk about flow predictions. How do we get bottom hole flowing pressures? And on top of it, I will talk about steady state versus transient flows. We may all know about reservoir transients, but we may also have wellbore transients, and I will throw it out there that liquid loading also, or casing heading can be considered as a transient phenomena. Well classification, we typically look at liquid dominant and gas dominant wells, and we see that in unconventionals too. Shale business started with focusing on gas dominant systems, and later on, after the collapse of gas prices, we moved on to liquid dominant systems and try to exploit those plays. The flow behavior in each will be, there will be similarities and there will be differences. Before going to those, I'd like to, in general, describe the flow, and flow patterns can be different for different wellbore configurations. Will be different for vertical configuration, it will be different for horizontal, and it will be different for deviated. In unconventionals, we can see all those three configurations. In the horizontal section, in the lateral, we may have toe up, toe down, and we may have undulated, slightly up, slightly down configurations. And after the curvature, we will definitely be ending up with vertical section. If we look at it individually, I'm not going to go and talk about them in detail. It will take a lot of time. However, I like to show you typical flow patterns or flow regimes for vertical upflow here and horizontal flow on the right. And at high liquid velocities and low gas velocities, what you may have is bubble flow. As you increase the gas flow rate, you will run into slug flow, and with large gas bubbles and liquid slugs alternating. And then as you further increase the gas flow, you will have irregularly shaped gas pockets and liquid regions, and this is called churn flow. Further increases in the gas will result in annular flow as shown here. Liquid will be flowing in the film and also as droplets in the gas core. For horizontal, at low rates, what you will have, liquid flowing at the bottom and gas flowing up top. At low velocities, again, liquid will flow at the bottom and gas flow at the top. This is gravity segregation. As you increase the gas flow rate, interface will be disturbed, and disturbance will grow and create the slug flow. And this is again close to slug flow in vertical flow from intermittency perspective. As you increase the gas flow rate, you will end up with annular flow. Again, I mean, there are similarities, but there are also dissimilarities. For example, stratified flow would not exist in vertical configuration. If we focus on oil dominant systems, pressure losses will be primarily gravity dominant, which will require the accurate prediction of holdup in the wellbore. There are predictive tools for pressure gradient prediction. They are put into two categories, correlations and mechanistic models, and you can find those in most commercial simulators. What are those? Correlations, I'm pretty sure most of you are familiar with Hagedorn Brown, Beggs and Brill, Duns and Ross, and you can add more to it, but all of them have a commonality. They are based on limited amount of experimental data, and they utilize very high level physics to develop the correlations. Our use of the correlations is an extrapolation exercise. We are definitely out of the development region. We are out of the data that is developed, that is used to develop the correlations. We are extrapolating, not interpolating. And that process will be inherently hit and miss. It may work, it may not work. And accuracies of the predictions will also be case dependent. To overcome those shortcomings, industry and academia worked on mechanistic models, which are honoring the physics better. However, in this approach, there is still significant amount of empiricism. What I would say, empiricism is simply pushed down a level. Some examples of mechanistic models, Ansari et al., TFFP unified model, Olga S., and later steady state. There could be a lot more. This is not all encompassing. I apologize if I didn't mention some of them. They typically perform better than the correlations. One thing that I like to point out, our real problem is going from wellhead to the bottom hole. But that is, that requires wellhead pressure measurement and flow rates measured at the surface, and then we work our way backwards. Since most of the gas came out of the solution, we start with two-phase flow correlations and start to go down. Typically, two-phase flow correlations have higher uncertainty compared to single-phase flow correlations. If you start with uncertainty, you continue propagating that uncertainty all the way to bottom of the well. And your uncertainty will be significantly higher than what is reported in the papers describing the correlations. Because all those papers describing the correlations following from bottom to top calculation approach. I'm going to go to gas dominant flow behavior. It is typically frictional dominant as opposed to oil dominant systems. However, gravity cannot be ignored. It is still important. How do we make the predictions? We use correlations and mechanistic models again. Correlations, all of the correlations I presented in the liquid dominant case are still applicable. However, the one that I did not mention because it is specifically applicable for gas dominant systems, gray correlation, seems to do better than the others for most of the time, which is proven with many comparative studies. Mechanistic models, again, would work for gas dominant flow behavior. All of those I talked about here up to now is for steady state flow. There's no change in the behavior with time, or there's no liquid accumulation. If we go to little bit of liquid accumulation case, what I'm talking about is gas well liquid loading. I will talk about that a little bit. What we have, gas coming from the formation. Initially, we have annular flow and no liquid loading, but as time passes by, our rate from the reservoir declines and ability to lift the liquids up in the well will be diminishing. And through phases, what we can have a complete stoppage of gas production and fully unloaded well, as shown on the right. Sources of the liquids in gas wells, it could be formation water, it could be condensed gas or condensed hydrocarbons. As I alluded a little bit earlier, liquid causes, accumulation of the liquid causes problems because it imposes a back pressure to the formation that typically results in flow rate reduction and ultimate, which we don't want, well may die. The others that we may be ignoring, but we need to pay attention to, if we have liquid accumulation at the bottom of the well, liquid may imbibe back to the formation, which would reduce the relative permeability. And basically you are damaging your formation by the liquid. And the other thing, especially important for horizontal wells, you may have severe slugging because you have a long lateral, and you have also the backside between casing and the tubing. You have enough volume for gases to compress and decompress, which will result in pressure fluctuations. And that would also have ramifications with respect to fracs and how sand migration might happen because of pressure fluctuations. If you mobilize your sand by slightly opening and closing your fractures, you may be losing also permeability or deliverability because of that. Timeline for production. I think Brian alluded to that a little bit in his plots. It will be different for each well. Unconventionals would have typically 2 years of lifetime, maybe longer, if we properly design the artificial lift techniques. And this chart is taken from Bondurant et al.'s presentation, and people can update this, but the message coming from here that our life cycle in unconventionals are really short compared to conventional wells. How do we identify liquid loading? You can identify liquid loading by observing your wells, looking at pressure behaviors and looking at oil and gas production, monitoring tubing and casing pressures. However, how do we predict liquid loading? There are many ways proposed in the literature to predict liquid loading. Primarily, what I would consider it as deviation from annular flow behavior. A gas well typically operates under annular flow configuration. If we deviate from annular flow, we will be observing liquid loading. How do we predict deviations from liquid loading? It would be looking at droplets. If they are flowing downward, dropping, then we will have liquid loading. If the liquid film goes in the other way, we will have liquid loading. There are many different models, and most famous of all is Turner model for vertical flow. There are other corrections to Turner for many different reasons, for many different configurations. For deviated wells, there are several of them available. Film-based models, Turner proposed one, but mostly we like to use Barnea, which is valid for all deviation angles. I'm going to go to steady state versus transient flow. I have talked about severe slugging. I'm going to show you a video for severe slugging. I hope it plays here. This is taken from an experimental facility at the University of Tulsa. This is your vertical section. Right now, the color is lighter, indicating that a lot of gas in the liquid. What we're going to be seeing in a second or so, the blowout will occur, and after the blowout, liquid will accumulate at the heel. This portion is toe up, resembles toe up section of the horizontal well. As you see, liquid is accumulation in the toe up section. And what will happen, this will be pushed down as the pressure builds up in the upstream of the toe up region. And that will, okay, in any second it will continue to go down. And then as soon as we hit the heel, it will blow out again, and this cycle will repeat itself.
And we have about 3 minutes left.
Sure, I'm wrapping it up. And the pressure signature, this is very important. You can observe this. It is cyclic and it is very significant. Can we see that in unconventionals? Yes, we can. This is taken from Sutton and Cox presentation. It is showing the severe slugging envelope with blue. And this is for a typical Permian well. And it shows us that we can get into severe slugging. And you can look at, with the common tools, you can look at what type of flow regime you can have depending on configuration. This is on the left, 1 degree up. On the right, we have 1 degree down. 1 degree up, we have slugging. 1 degree down, we have stratified flow. Similar plots for 90 degrees. What I would like to say, we can predict the liquid loading initiation when we have heading or severe slugging. However, we do not have a simplified, accurate, and easy to use models to predict the hydrodynamic behavior of liquid loading or with liquid loading. All-purpose commercial, transient commercial software are available. They are originally developed for flow lines. They have shown their predictive abilities, which may be used, but they are also very pricey, I might add. With that, I hope I have been able to give you a picture of the state of the art in wellbore flow, which is also related to unconventionals and horizontal wells. I would be more than happy to take any questions.
Terrific. Thanks, Jem. Oh, yeah, we've got a few questions here. The first one is there any industry accepted method for calculating bottom hole pressures for coal bed methane wells? And I think we're talking about where we're pumping, water up the tubing and gas up the annulus. What would you recommend for calculating bottom hole pressures?
Are there any isolation of backside from the tubing?
No.
No, and then I think you can either use the backside or the tubing side using conventional, accepted industry correlations. You can pick the ones that you like. I'm pretty sure you can adapt any commercial software to do that for you.
So if I understand, for the annulus, we do our gas calculation down the backside, and then once we reach the liquid level, we would do a different pressure loss calculation below that.
Yes, you need to know the liquid level, and you need to have a backside test to determine the, you need to shoot a sonic log or have echometer type logging to obtain the level. And up to that level, you can use single phase gas, and then below that, you can use single phase liquid hydrostatic calculations, and that would be the easiest. However, you can still use the tubing side, knowing the rates. It might give you a little bit more uncertainty in your predictions.
Right, as long as there's not a pump preventing that communication.
Correct, correct. But if there is a packer, you don't have any other way but go to tubing side of the thing and then calculate the bottom hole flowing pressures using a correlation.
Great. Okay, the next question, I think this question actually came in a little bit late for Brian's talk, but anyone is welcome to answer this. The question is, in your opinion, what are the costs that would increase more at the end of the life cycle of a well? And what would you recommend for companies to keep profitable operations? So anyone can answer this.
I think there are different artificial lift methods available. There are limitations of that. I would recommend looking at all those, all of the above. You can use plunger lift. You can use surfactant lift or foam lift. There are combinations of gas lift and plunger lift. It all depends what you have initially in the well. If you already have gas lift apparatus, the only cost would be you need compressors to compress the gas and send it down. Plunger lift is maybe the cheapest. However, it would require still reservoir energy to be employed. If you deplete that, you have to come up with creative solutions, supplement the plunger lift with other techniques, maybe use surfactants or a little bit of a gas. That's my 5 cents into the discussion.
Yeah, I think that's absolutely correct. From my experience, the costs that tend to increase over time are going to be your chemical treating costs as you start to have scale issues form in your tubing, and also corrosion issues if you're in that kind of a reservoir environment. So typically your chemical treatment costs will increase. You need to have a good understanding of what your scale inhibition and corrosion inhibition program looks like and its effectiveness, and whether you need to ramp that up or down over time. But then also probably the biggest one is, as Jem mentioned, is the artificial lift and doing all of your due diligence. And this is really kind of the focus and what I see the value in RTA for production engineers is those reservoir models that we ultimately derive from RTA allow us to do our due diligence to optimize and run scenarios on each of those forms of artificial lift. And that then enables us to understand what is the cost to install that artificial lift, what is the uplift we should expect to see from it, and what does the payout look like for that incremental uplift that we're going to see. And so that's kind of to piggyback off Jem is what I would say are the costs that increase and how you can mitigate those with RTA and a good reservoir model to keep them as low as possible and to extend that economic runway for your wells.
Thank you. One more question here is, what is your opinion of the use of blow cases? Many operators use them to increase uptime, but end up creating very noisy production data, kind of an artificially created slugging.
Blow cases, can you explain it a little bit? This is the first time I'm hearing. Are you opening the wellhead to the atmosphere? Is that what is done to unload the well?
I was hoping you would know what blow cases means, because I haven't heard the term before.
I have not either.
Okay. Well, if no one else has any ideas, we'll just look into that and follow up later with the
the sure.
Another question is, can you talk about automation or digitalization happening in the artificial lift domain?
I would defer that to Brian since he has more experience in the field and might have a better a pulse of the industry. I'm pretty sure automation will be will happen in the context of reducing the cost of production. But where is the break-even point? How we're going to get there? I think that is the big question. Automation may not mean always may not translate fully to cost reduction. Brian, would you like to chime in, or anybody?
I think that's absolutely right. We're already seeing digitization and automation and some of these advanced techniques, machine learning and AI, start to influence the techniques around characterization of decline curve analysis, B factors, things like that. They'll probably continue into the production engineering realm with selecting appropriate correlations for use and estimating multi-phase flows over the life of the well. But specifically related to artificial lift, I do think there is that breakover point that will have to be considered. You look at something like an ESP, typically we're going to be getting measured bottom hole pressure data from an artificial lift form like that, where something like plunger lift may not need it, but you are seeing smart plungers come into the market and trying to get as much data as possible. But the cost of those installations and data really has to be screened. When you talk about taking over stripper wells, you're probably going to have to do more with less. So it's going to be relying more on the old estimation techniques of what's the differential between casing and tubing pressure looking like? What are my arrival times if you have a wellhead sensor? So I think there is that trade-off point. So I think it's going to be big for influencing the role of production engineering and a lot of the technical work. And there will be, in kind of the middle life of the well and optimizing artificial lift, there will be a strong push and movement into digitalization and automation of artificial lift. But as these wells continue to decline, I think you're going to have to see some of that disappearing and going away to continue to make the wells profitable once you kind of have an understanding of the performance.
Great. We do have a lot more questions, but I'm going to keep moving to the next presenter just so we make sure we can get that completed. And then at the very end, we'll answer all remaining questions that we have time for. Awesome. So our next presenter is James McDonald. And James started his oil and gas career in 2002 with Schlumberger wireline logging services, logging wells throughout Western Canada and the Arctic. 12 years ago, James joined Fiquet Associates as part of the sales and development team, and he actually helped create the original Harmony software. Back in 2012, James moved to Houston with Fiquet, who is now IHS Markit, and he became a full-time instructor. So through James's career, he's taught over 100 in-house production data analysis courses, focusing on unconventional rate transient analysis and reservoir modeling. Now, something you might not know, James would much rather be fishing, but he says that he's not able to catch enough fish yet to pay the bills. So he's still doing the 9-to-5 thing. So with that, I'll let James get started with his talk.
Oh, I wish you had more pictures. I was enjoying that. Thank you, Graham, for the introduction. Again, I like the pictures. Thanks for the talk, Jem. Definitely some things in your talk that relate to some of the scenarios and what I'm going to be discussing. Brian as well, good talk. I didn't know you were a rugby player. I also played rugby 20 years and 60 pounds ago. I noticed that Zoom's actually making my screen a little bit narrower than everybody else's. So if it makes me look thinner, then we're all winning. All right, so I'd like to thank everyone for inviting me to be part of this webinar series. To start off with, I love the idea of focusing on how tools that are generally considered to be more part of a reservoir engineer's toolkit can and should be used by more production engineers. So for this talk, I'm going to focus on the transient and the multi-phase aspects separately to discuss their issues with each one of those categories, and then I'll bring it all together. So my kind of like mission statement or the goal for this talk and the goal in general is to build trustworthy deliverability curves that we need for important decision making. So I'll start off with a quick description of the deliverability curve. Considered to be, I don't know, I guess the way that I like to describe it is that it's just a convenient and simple way to describe a well's potential. Right, so if you give me a back pressure, I can give you a rate. Give me a back pressure, give you an estimate of a rate. So this line that you see here, our deliverability curve, would be considered more of the ideal deliverability curve, right? So it would be, the shape of that line would be an indication of a system that would have an incompressible fluid, single phase. So more, another way to say it is a constant productivity index. Unfortunately, it's not a curve that we tend to see in real life. So if we look at some of the more common methods that we use to describe a IPR curve, used widely for gas wells is the Rawlings-Shellhard method. And you can see there's a lot more curvature here to this curve. Vogel, again, a very, very popular one on the oil wells. So you tend to see more of a straight line once you're above the bubble point, and then once you're below the bubble point, the curvature kicks in based on the equation that you see here. I really like this slide because it just kind of gives a quick description of the different things that can affect the departure that you would have from what you would expect to be an ideal deliverability curve. So you can see in here that multi-phase flow is certainly one of those categories. Skin or maybe conductivity issues come into play, and then throw in some reservoir effects, geomechanical or compaction issues you might see in the reservoir. So then consider that kind of the introduction as to the deliverability curve, right? But there's no denying that it's certainly a very important, widely used tool to help us in our decision making. So, first big topic, what's the issue when working with transient flow? The problem is that if we're looking at using one of those common methods, Rawlings-Shellhard, the Vogel, or any of these other common methods, there's an unknown that we're looking for here, right? What is that average reservoir pressure? Because it ends up being a very important part of these equations to build the curve, not just where it starts, but what that shape of that curve is going to look like. So then to the question, what is the average reservoir pressure in a transient system? The answer is somewhere between I don't know and there isn't one, right? Is a good way to describe it. So that'll bring us to our first example. This was actually a question that came up a few years ago. After I run tubing, my well produces noticeably less than I expected, right? What's going on? So here for this particular well, here's the pedigree of it. It is a gas well with about 8 months of production. Initial reservoir pressure was 5,000 pounds. And I put this plot on here to show that this is one of the most commonly used tools by reservoir engineers today, especially when dealing with unconventionals. There's a lot of information you can get from this particular plot, but just visually looking at it, what I'm seeing is that this is showing a very strong linear flow signal, or even more importantly, for the sake of this conversation, a very strong transient signal, right? So it's one of the things you can get from just looking at this plot, the behavior of the data. So additionally, this well has well spacing about 1,000 feet, so there's a lot of area on both sides, and then flowing at about 5 million a day at the wellhead, and then 800 pounds of wellhead pressure. So if I was, and this is what would commonly be used today by a lot of production engineers, to use the Rawlings-Shellhard method and generate this deliverability curve, basically plug that information into this equation to build this curve. I want to point out that one of the things that I did here, because I've heard this in conversation as well, is that if you are transient, you believe that you're transient, one of the things that you can do if you don't know what your average reservoir pressure is assume that it's the same as your initial reservoir pressure, right? So I don't mind that idea if you're a couple of weeks into the life of the well, that's fine. But the idea of using that if you're 8, 12, 18 months into the life of the well, stay away from that, right? Turn the dial, leave the room. That can certainly lead to issues in trying to predict the behavior if you're trying to account for what would happen if you impose an operational change on the well. So for this particular scenario, I'm flowing up casing and I'm planning on running tubing. So here's my tubing performance curve for my casing flow. The way we show these curves the dotted to a solid line transition is where you'd expect unstable flow to occur, meaning that this is where my curve is telling me, for this particular case, that I'm going to drop below the minimum critical rate as defined by Turner on here. So my goal is to have operating points, how I'm currently behaving, to show up on the solid part of the curve. And it's happening here, but the problem is that in the not too distant future, I would expect to potentially get into an area where I'm going to get unstable flow. So then my goal would be to run tubing, right, as one of the artificial or one of the additional methods that I can use to extend the life of my well. Run tubing. So the first thing that you see is that unstable flow region is significantly reduced, so I could flow this well a lot longer. The other thing is it gives me a new operating point. So what do I expect to see is about a reduction in about 500,000 a day on this well, mostly due to the additional frictional loss in the tubing. But the issue is that when I actually did the work, or when the engineer did the work, and they ran tubing, the well came on at significantly less than what they were expecting, right? So that's when the phone rings, like, what's wrong with your friggin' software? It turns into, I'll deal with that Monday issue. So to dig into this a little bit further, the work I'd done to take a look at, get a better understanding of what's going on, I built this spreadsheet just so I could get an idea of what my depletion is in the area that I've investigated in time. So I use this to figure out how far into the reservoir I'm seeing every day, and then I take out the volume that I produced every day to give me to try to calculate an average reservoir pressure for the depleted region in time. So then when I did that, and because I have to iterate on multiple points, I didn't do it for every single day. It took a long time just to get to that point. These points here represent what would be considered the volumetric depletion for the area investigated in time. And then the blue line at the top represents the volumetric depletion if I assume that I'm draining the entire reservoir the whole time. You can see there's a big difference here, and that really points to one of the big issues with transient flow of trying to help determine what your average reservoir pressure is. And I'm not saying that what I'm doing is perfect and right and will give you the right answer, but the goal is trying to get you closer to the right ballpark of what that number should be. So going back to our case where I build my deliverability curve and I overlay my casing flow curve, when I take my new estimate of my corrected average reservoir pressure, I get my new deliverability curve. So then if I take that same tubing performance curve and I throw that on there as to where I'd expect this, would I expect this well to behave with that operational change of running tubing, it gives me a much more accurate result as far as how the well actually did behave in that case where I was wondering why did I lose so much more gas than I was expecting.
James, just halfway mark, by the way.
Sorry?
Halfway mark, by the way.
Oh, thanks, Graham. So that's our transient portion. So I'm going to focus a little bit more on, the multi-phase. So first bullet point, big topic, right? Big topic, a lot of information out there. So I want to start off by just putting up this flowing material balance plot up here. So the flowing material balance plot should be considered part of the backbone of production data analysis tools that engineers use when performing rate transient analysis, right? So if the goal is to try to get more production engineers to want to use more RTA type tools, this is certainly one that would show up. The idea behind using this is fairly simple. Plot my data, my normalized rate over normalized cum, and then the extrapolation of this late time data should point to an estimate of an original fluid in place, right? The reason it's so popular is that it's so simple and easy to use, and it gives you very valuable information. But what I'm using it is to show you, I'm going to use it to show you what a multi-phase system, mostly dealing in this case with an oil reservoir dropping below saturation, what that can do to the data on a plot like this. So I simulated a case where you can see everything seems like it's point and fine. Because I simulated it, I know the size of the reservoir. So I'm pointing at that here. And then the data seems to be, everything's in agreement at this point. But I flowed a little bit longer, and now I get this behavior. And if I flowed a little bit further, I was like, oh my goodness, what's happening? You're losing that ability to flow that oil, right? Like losing all that energy from the gas being liberated from the oil. And it can do very awkward things to your data, making it hard to interpret what's happening when using some of these tools. So I'm using that to introduce that there's a lot of literature on this topic. There's a lot of information out there, right? One of the papers that I really like, this one here that you see, talks about dealing with multi-phase, starting off with water and oil, and then gas is going to come into it once you reach the saturation point, and then gas coming into play. So the three categories here that you can see is, well, what if you have water in different lenses? Well, it's kind of hard to deal with that because you never know really where the water is going to be and if you're going to hit it or not. So we'll avoid that one. Move into, if you have oil and water and you believe that they're separated in individual layers, well, then the idea there is fairly simple. Go ahead and analyze each layer individually, and then just add the results together, and that tends to work fairly well. But then the more complicated and the more really important case for our talk is, what if you have oil and water taking up the same pore space, and then gas is going to also then come into it. So what I'm introducing is how you can, there's been a lot of work done at trying to modify these historically single-phase tools to make them useful for multi-phase conditions. So for example, so I guess really what I'm alluding to is, for a way that we can help use this tool to help benefit us is to take, for example, this oil, this normalized rate, which would be your Q over delta P. That delta P is your PI minus PWF. So instead of using those static pressures, those static values, modify those. So that we introduce the pseudo pressure term. And really opening that up to pseudo pressure allows you to just add a whole bunch of things in there. So instead of using the static pressure, use pseudo pressure. What's inside, what we can put inside that pseudo pressure term would be your changing properties, right? You're changing compressibility, you're changing viscosities. Another thing that you can throw in there, and this is where it really becomes important with multi-phase, and that's why these equations are here, is using this information to account for the changing relative permeability of your fluids, using your producing volumes through time. And then something else we put in there after when we introduced the pseudo pressure for oil was the reservoir issues of compaction, right? A geomechanical curve, throw that term in there. So really what it is open up pseudo pressure as an option and just throw a whole bunch of stuff in there to really help you out. So then this slide here describes and shows you when you go from just leaving everything single phase, looks exactly like the same plot that I had, and then you start applying these corrections, it can take your what ends up being unusable data and turning it into something useful that can still help you make more relative decisions about your well or learn more about your reservoir. I guess the other thing that's worth quickly pointing out is that without the corrections of even just the actual properties of that oil, we were significantly pointing to a much bigger reservoir than we actually had. So in addition to just fixing that bottom part of that multi-phase behavior, we're also able to much more accurately predict the size of the reservoir. All right, so the point of that was to talk about multi-phase flow and how it can affect your ability to interpret data in rate transient analysis world. So back to deliverability curves. If our goal is to build a deliverability curve, I'll even just say it this way, why not use a tool that can handle your changing in fluid and rock properties? Why not use a tool that can account for the different flow behaviors, so the relative permeability curves? Why not use a tool that can account for your different completion design and gives you an idea of, and accounts for how far you've seen into the reservoir? That does all of this for you, right? So then the answer here, like the point of really a big part of just this talk in general, is you need to use a numerical reservoir model. And not to scare people that don't do a whole lot of reservoir modeling. I'll talk more about it as we go on, but I'm going to show you the benefits of doing this first and then talk about it here a little bit more. But that's the point. You need to use a numerical model. So this is a paper that was published this year by the engineering team at IHS. So the first thing I want you to look at here is the shape of the data, because that's really what becomes important, right? The shape of the information, the shape of how we would expect to help predict the behavior of a well, depending on what we're planning on, even just how we think it's going to behave as you're forecasting it out. But if you're looking at making an operational change and you need a deliverability curve to help you with that, the shape of that curve can be a lot different than what you would expect it to look like. One of the things that came in here that was interesting, that when you're dealing with just linear flow, so again, a strong transient signal, once you reach the bubble point, you could actually see a bump up, right? A kick upwards in your production. which when you compare it to a conventional IPR. So that was interesting. You see in this plot here beneath that a lot more shape to the data. You see that bend backwards, almost similar to like that flowing material balance plot. But then you can see some weird things kind of happening. I'll say conventionally thinking when it comes to a single phase world, oh, sorry, I thought I saw Graham give me my quick warning here.
Yeah, 2 minutes.
Okay. If you increase the drawdown, you increase the rate. Increase the drawdown, increase the rate. You see that happening here. But really what we're saying is that in a multi-phase situation, you increase the drawdown, you might increase the rate. But if you increase the drawdown more, you might actually decrease the rate. So it's something worth considering. So in addition to, this is just accounting for the actual properties of the fluid that you have. If you actually bring in, say for oil, so if you bring in the relative permeabilities into it, what they did was show, and what I think becomes very important, is a sample set of taking different fluid conditions and relative permeability conditions to coming up with all these samples of how the information can look. So really what I'm saying is that this is how we need to start thinking when we're making operational decisions of predicting future behaviors for our wells, right? Get out of just the conventional curve that can lead you into the wrong direction. This is more of the type of work we need to really start doing. So I'll go through this really quick just to get to my last point there, Graham. So these two papers, I use them to introduce kind of the last big component. So really what I'm telling you is that all the tools, all additional tools, reservoir engineering tools, whatever you want to call them, rate transient analysis tools, are very valuable for helping you get to that reservoir model as well, get an understanding of everything that's happening. So let's say you're at the point where you've got your model and it is history matched. So then the question is, well, how do I use the model to actually build the curve, right? How to generate that curve? The answer is simple. You essentially, once you've got the model built, you forecast it out. So this covers two different categories. One, how do you forecast it out? And then two, what's the time component? So the time component is a big part of this too. How long do you forecast it out? So in this paper on the left, does a real good job of going really deep inside of, really introducing that time component. And they really, it's a very rigorous method of doing simulations for your inflow curves and your outflow curves and how they converge. And it really goes deep into it. So it's a good read, but even the paper on the right even references this paper to say that what they're doing is good, but we might be able to simplify it and make it a little bit more usable in this paper. And then the one thing that this really points out is that so you've got your model, you have to forecast it out. You can forecast it out a bunch of different ways, and that's really what they talk about. You can forecast out at constant rates, constant pressure, ramping rates, ramping pressures, and there's variation in the results that you get from doing that. So then the time component comes into play of, well, how long do I forecast it out? I'll say there's a relationship between the permeability of the reservoir, how tight it is, and that time component. So I'll say some of the work that we've done when we're dealing with really, really tight reservoirs, say like a Marcellus well, the forecast period that seems to work out really well is somewhere between like 100 and 120 days, right? So for about 100 nanodarcy rock. That being said, for a higher permanent reservoir, you would think that you should have to bring that back a little bit and not forecast it out as long. So somewhere in that window. So the sensitivity, so where it comes on to you doing this type of work, is the sensitivity of how much time to run it out for is something you'd have to play with. Right? But if I'm giving you a bracket of somewhere between 0 and 120 days, that's a nice window to kind of start in and see what works. So you run this on a couple of wells, you start getting a feel for that time component, what that should look like, and you should be able to start keeping that consistent if the rock's not changing too much for a larger group of wells. So then that being said, here's my example of when doing this. So I've got this well. So if I'm going to use the Vogel method here to calculate a deliverability curve and then compare it to the actual reservoir model results. So I've got a rate, right? My oil rate, I've got a bottom hole flowing pressure. This teal blue curve you see here is a example of a volumetric depletion. Again, the idea that I'm draining the entire reservoir at the same time. So it could be wrong, it could be ridiculously wrong. The more time you have, the closer to the right answer it'll be. But so just be very skeptical of, trusting a fully volumetric depletion number when doing this work. But really to say that I went in there and I put in the numbers, and I ended up getting this deliverability curve focused on the Vogel method. So then, but to actually do the work of everything that I'm describing using the reservoir models, what you end up with is these points. I know they might be a little bit hard to see. I'll apologize for that. But these points represent me forecasting the reservoir. So the option that I chose, constant rate, constant pressure, ramping pressure, combinations of some of these. For this, I just focused on a ramping pressure, right? I just ramp my pressure to different pressures, get that relevant rate that comes from that forecast, and then that's the XY coordinates that I'm using to plot this curve. It becomes really easy to use, but you can see how it becomes a little bit manually intensive of having to do that work yourself every time. To use this in our software, to actually make this usable as far as plotting tubing performance curves on there, you then end up having to draw a line. So the line is a best fit that's trying to go through the points based on any of these methods that you see here. But I do have to give it an average reservoir pressure, right? It's just not going to plot a line without an average reservoir pressure. So then I modify this number to increase and decrease it until I get something that goes through the meat of the data as good as possible. So that's just as far as using the software right now. But the goal should be that you don't need to use an average reservoir pressure, right? That you just get these points and just draw a line through these points, and that's your deliverability curve. So then comparing those two methods again, I knew I was probably high on the high side of building my curve with Vogel here. You can see again that big gap in what the average reservoir pressure is, but I don't want to focus too much on the actual average reservoir pressure term and what that number should be, because in a lot of the literature that talks about this as well, even outside of what we've worked on, is don't worry about average reservoir pressure. These points are really what's important at this point. So then in closing, that point that I just made, you don't need your average reservoir pressure. It doesn't become something that you have to figure out what it is because you're not using those common methods, the Vogel, the Rawlings-Shell-Heard, and the other equations that are out there. Say a computer is a useful tool, right? So the whole idea behind where, there's a lot of stuff going on, the changing properties and relative permeabilities, compaction issues, and reservoir effects. You use the tool that's doing all of that, taking all that into account for you, right? So a little bit more learning on the front end of a little bit more transient reservoir modeling world. And again, I'm talking to the production engineers, but it makes it much more technically accurate to help you make better decisions. So my plug, in the not too distant future, all deliverability curves will be generated from reservoir models, right? I honestly believe that. The tools nowadays are becoming so much more efficient, easy to use, and relative for the types of fluids and reservoirs that we're going after. That, and why shouldn't just go in this direction? Why not use a reservoir model that's doing all the work for you and give you the option of being much more accurate in the decision making that you're trying to accomplish? So then that plays into it. So a fundamental understanding of rate transient analysis is a necessary skill for all production engineers, right? So I didn't say it could become, as I'd say today, it's important for production engineers to spend more time learning more about the tools that, again, that I said at the very beginning, are considered more reservoir engineering, parts of the reservoir engineer's toolkit. So, last point, numerical models generated, a numerical model generated deliverability curve will be released in Harmony Enterprise in February. So I'm not giving you all this information and telling you now you got to go build a whole bunch of spreadsheets, right? We are expecting to be able to give you the tool to do a lot of this for you in the very near future. Mario likes it. And if you think this guy's excited about that, look at the guy behind him. That guy is excited. So, yeah, that was my last slide.
I laughed. Good job, James. So we have about 10 questions, and just for you, James, I'm going to try to read the ones that are relevant to your topic, okay? And then for the remaining ones, we'll cover them at the very end, okay? So,
sure, yeah, and I think I might have went over time a little bit there, so I apologize for that, but that's what you get when you get me.
Okay, well, we'll get through these. So the first question is normalized rate versus cum plot technique, what is the normalizing factor? And I think, James, they're talking about the flowing material balance, I believe.
Yep, sure. When we say normalized rate, I guess the term normalized rate, normalized pressure come up an awful lot. And really the difference there is just if it's Q over delta P or delta P over Q. So that's the normalizing there. On the normalized cum, the normalizing action there is actually the pressure is actually involved in there as well. I think even in the papers that I reference, actually one of the papers that I reference goes to a great detail of the flow material balance and shows you all the parameters. There's a little bit more than what I just threw in there, but it does that one paper that's in there does a great job just going through the details of flow material balance and shows you everything that's in there. But
Yeah,
I'll say
so
the normalizing factor is mostly pressure.
So maybe after we'll include like a reference for more details about the FMB in the follow-up.
Sure.
The next question is, why would the AOF of a well increase as reservoir pressure declines?
Oh, good question. Because that was, I know for the work that Ahmed and Moran and Jesse and all the people that worked on that paper, that was kind of one of the big eye-opening things when they were doing a lot of their testing, that especially you're still declining your pressure and you're going below the bubble point, but why does it increase? And and I don't have the perfect answer for you, but I will say there is a combination of being in linear flow, reaching below the bubble point. It was one of those eye-opening things that said like, wow, this is something we didn't expect to have happen. A lot of the work that they did, part of why it's like, a lot of the research has been happening for a while, and it's still taking a long time for us to actually get everything into the software for you, is we actually learned a lot about the model, a lot of updates, a lot of changes that we had to impose in the reservoir model to make it behave properly. Actually, doing a lot of the work taught us maybe where we were limiting ourselves in the ability to account for the proper fluid and fluid transfer equations in the grids. And so we've done a lot of updates to the model based on the work that we did in this research. But I'll say, as for the short answer would just be the transient effects, right? The transient component of the data could cause it to have that unexpected shape when you see the bubble point in your deliverability curve.
James, I think you'd also agree it doesn't increase in every case. There's just certain combinations of fluid properties, drawdown, where it can happen, right?
I think that's a good way to say it. That we noticed that it was happening and then documented it.
Mm-hmm.
So I guess another example of using a reservoir model to build a curve for you should be considered, I'd say, more technically accurate and can lead you to seeing results that you wouldn't have expected to happen.
Okay. Cool, James. I've got two more questions, and then we're going to give it over to Dave Anderson. So it says, can you please explain how the rel perms are affecting IPRs shown in the paper? And James, I know that would probably take a long time to explain, so maybe we'll just link people to the paper as a follow-up. What do you think?
I like that. That's a big question, but it's a good question. I'll say the one thing I'll just talk about relative permeability curves is I talk about relative permeabilities in a lot of talks that I give, and like often a question that always comes up is some variation of how do you know what your rel perm curve should be set to, and it's one of the biggest question marks out there. Right? There's testing and things that you can do to try to learn what those curves. There's a lot of literature, a lot of information, but it can be a bit of a question mark, a big question mark when doing numerical modeling as to what those curves should be. And that's kind of like a blanket statement to say that it can be tough. Like predicting what your net pay is, predicting what your relative permeability curve should be set to, kind of falls in that category that we need to work on this.
Great. Okay, I'm going to save the last question for at the very end, James. So thanks.
Sounds good.
All right. So next, I'm going to introduce David Anderson. So David is the co-founder and CEO of SAGA Wisdom, and it's a technology. Sorry, I just lost my slide here. It's a technology company that specializes in practical on-the-job training for the oil and gas industry. So David is a recognized authority in the discipline of rate transient analysis, and he's actually one of the original architects of Fiquet's RTA software, which is now IHS Market Harmony. And that's just the industry standard as far as production data analysis tools goes. So David was previously the director at Anderson Thompson Reservoir Strategies, which was an NCS multi-stage business, and he oversaw a multidisciplinary reservoir advisory team that supported all of the completion side of that business. Now, before that, David was actually a managing partner at Fiquet Associates, and he helped build a multi-million-dollar petroleum engineering software business there. David has over 23 years of petroleum engineering experience. He's taught training courses all over the world, and it's actually led to him being appointed a distinguished lecturer for the SPE in 2014. David has co-authored over 40 technical publications. He's been on multiple programs and technical committees with the SPE. One thing you might not know about Dave is that he knows the name of every capital city in every country of the world. And I challenge you to quiz him on that when you run into him. And he's also a really good drummer. So Dave, why don't you take it away?
Oh my gosh, thank you, Graham. I hope no one calls me on that one now. I used to know them all, but I'm not sure that I do anymore. Thank you very much for the kind introduction, and thanks to all the panelists and attendees so far today as well. It's been a great session so far. Let me just share my screen here. My talk is entitled Identifying Candidate Wells for Intervention and Quantifying Upside. And really what this talk is going to be is just a series of examples. I'm going to show you, I've handpicked some, what I think are interesting examples over the years of production data where we've been able to use some fairly straightforward reservoir engineering principles to try and identify production optimization targets. So just start with some, what I think are some good guidelines to use here, important guidelines for production engineers. Every well should have a clearly stated performance expectation and not just a production target. You're going to hear me say this over and over again. Really what makes production engineering connected to reservoir is the flowing pressures. So when I talk about a performance expectation, it's not just, we want a well to produce at a certain rate. We're really talking about its deliverability, which of course includes flowing pressure as well as just a production rate. And I'm going to say, and I think most people would agree, that most wells will fall below that expectation. That's somebody showed, I can't remember which speaker, but somebody showed an IPR curve that showed the ideal IPR. I think it was James, and then the practical situations where well production falls off that IPR curve. That's the reality of the situation, and that chance of lost productivity increases with time. So the longer a well's on production, the more chance that you're going to fall below that ideal situation. Productivity loss is not always obvious. So just simply looking at your production, you're not always going to be able to see. And I'll show you some examples of where that's becomes very clear. And the importance of bottom hole pressure measurements cannot be overstated. I'm going to show you a couple of examples in my talk where we really can't get good resolution without measuring the bottom hole pressure. And of course, that's something of a rarity in the industry now, and is even more important with liquids-rich plays and oil reservoirs. We really need to understand that bottom hole pressure measurement. There's a multitude of opportunities for low-cost intervention with high impact results. I'm just going to show you a handful of examples that we can identify. In 2016, I came up with this idea of a well doctor. And my thinking here was that, thinking of your well as a patient is a very good analogy to what we actually do in the field in production and operations. And so the idea is you assess the, one specific analogy I can give you is like cholesterol, right? You go and see a doctor, get your blood test, and you have this sort of baseline for cholesterol. If you don't have the baseline, you don't really know what to expect. So measuring it the first time gives you that baseline. And then you go in year after year and you measure it and see whether your cholesterol, for example, is spiking above that in a dangerous way. And of course, then there can be some treatment that goes along with that. So that idea, I think, has some value, treating it sort of on a well by well basis. So I'm going to show you some examples where we do that. You can conduct tests to sort of do those diagnostics, and then of course we want to identify some suitable treatments. Sometimes the treatments are very straight, like as in the medical analogy, sometimes the treatments are very straightforward and easy. Sometimes they're much more difficult and risky. So we'll talk about that as well and try and categorize how those different things may come into play. And then the idea of triage, choose candidates for optimization. So here's my first example. What I'm showing you here is just two production rates from two different gas wells. And if I asked you to pick out which one is the, in quotes, the sick well or the unhealthy well, it would be hard to do that. I mean, you've got two wells that really are, over the time period that you're seeing, they've accumulated about the same amount of production. They both have some operational changes. It's tough to really see what's going on with only looking at the production rate. So this is probably the easiest way that you can bring RTA into a production workflow. This plot is very, very simple to do. You can do it in Excel. You don't need fancy software to do it. Of course, there's commercial software that will plot this as well, but this is just your standard diagnostic plot, square root time plot in this case. And what we see when we look at this is well number one has a sort of a fairly, what we call healthy response. This is the response that you'd expect from a well that exhibits transient linear flow. And there's some scatter in the data, as there always is, but there's a straight line behavior. In well number two, we see that there's this disjointed behavior. For instance, you have data shown here that makes a straight line, but then there's another trend, and we'll talk more about this later. I'm going to expand on this case a little bit later. But the discontinuity indicates that there's a significant production loss or productivity loss in that well. And in this case, we can trace it back to happening as a result of opening the choke. Another way to show this is with modeling, and James talked about this concept very well. And I think, again, I agree, I share his vision that the future of production optimization and production monitoring is going to be done with reservoir models. That's really the most efficient and rigorous way to do this. So this is a modeling exercise where we use the 5 months of production data, in this case, for example, to establish a baseline performance expectation. So we've got a history match of our flowing pressure, and these are 2 oil wells. And then what we're going to do, we get a good match in both of these cases. Now there's a lot of hair on this. There's a lot of work that has to go on ensuring that you've got a match that makes sense with all the information that you have. And I won't get into all the details there. But if we have a lot of confidence in this baseline model, what we can then do is forecast and monitor what happens in the future with the well. And again, we have one case where the well keeps in line with its assessed well performance. And then we have the second case where the data starts dropping below. And so again, you have this idea where one well is not reaching its performance expectation. One well seems to be reaching its performance expectation nicely. So let's try and examine a little bit further on this second well that wasn't reaching its performance expectation. Most of you would look at a plot like this and immediately identify what the problem is. This is a well that's a naturally flowing oil well, and you can see it's just dying for artificial lift, and artificial lift wasn't installed in time, I think, in this well. It probably should have been done, if not from day one, then certainly after a few months of production. There's not enough energy to lift the liquids. But I want to point out, to be sure of what's happening with this well, you'd really want to do a bottom hole pressure survey. So you'd want to get in there and measure what that bottom hole pressure is. We can't trust these calculated bottom hole pressures that are obtained from surface data, and Dr. Sarica's talk really pointed that out as well. That's going to be highly unstable transient flow in the wellbore, and we need to get down there with a gauge to measure what's actually going on. Excuse me. Here's an example from a gas well. Another, I think, what you'd call obvious example of liquid loading. This is your gas production data. When you start to see things, for example, like a sudden drop in rate, increasing decline rate, and accompanying this would be a loss in liquid recovery, that's a very good indication that you're losing or that you're starting to load up. An early indicator of liquid loading, as most of you know, is this idea of critical gas rate. These are sort of standard tools that I think the production engineer uses, particularly in the world of gas flow, gas facilities. And we can identify that, hopefully get an early warning system on that liquid loading, which will allow us to take the necessary precautions, for example, putting in a plunger lift or using surfactants or something to try and unload those liquids and prepare for the inevitable that's going to happen later on. Here's one that's maybe a little less obvious. This is an oil well in the Eagleford. And as you can see, we have an event here, an operational event, and it's not exactly clear what's happening. There's, other than the fact there's an increase in drawdown, that's your production or your flowing pressure dropping. And we have a corresponding increase in production rate, but then the rate starts to decline as well. So just looking at this data, it might be ambiguous to answer the question, did this lead to a productivity loss, or is this sort of what's supposed to happen? And we can really only answer that question with confidence, again, once we have a baseline model. And in this case, the baseline model matches the data up until about mid-February. And then we see a pretty significant divergence of the data from the model. This is a great way to assess productivity loss. Now, this isn't telling us what's causing the productivity loss, but it's giving us I think, a pretty good red flag that there's something wrong in this well. How severe is this problem? Well, we can answer that question by doing and again, you can do all this with reservoir models. You can answer that question by doing a side-by-side production forecast. In one case, do a production forecast with the as-is data, and you don't need a fancy model to do this. You can just use a decline curve to say, okay, this is what the well is on track under these conditions to produce, somewhere in the realm of about 290,000 barrels. Where you do need the reservoir model is to generate this forecast, and this forecast is what would happen if you had not, let me go back to the plot for a minute, if we had not changed our operating condition here, if we had just kept producing at this pressure under existing conditions. Surprisingly, or maybe surprisingly, I don't know, this answer surprised me. There's almost a 200%, 100% increase, or shall we say, a 50% loss, if you want to look at it that way, in total EUR by initiating this change in operating conditions. That's, of course, very, very significant. And it's not at all obvious when you look at this data before you do the modeling. So this is an example of an insidious problem in the sense of missed opportunity cost and missed value, that if you didn't employ the use of a reservoir model, you would never identify, you'd never even realize that you had a problem there. So that's probably my biggest plug for using reservoir engineering techniques, using reservoir models to get a better handle on what's going on in your production system. So a few years back, I tried to put together this kind of matrix of, in a way, categorizing different well performance issues and the well performance diagnostics and optimization tactics that would go along with each of those. And I've got them categorized broadly as surface, wellbore, and reservoir issues. And as you might expect, as you move from the surface upstream into the reservoir, the issues become more severe, more difficult to remediate. So the low-hanging fruit is typically on the surface. So let's talk about some of those surface problems. Here you have things like low pump efficiency, insufficient compression, pipeline capacity, things like that. These tend to be fairly simple problems, and I'm going to show you an example of one in a minute. And we can assess the symptoms usually just by looking at the production and flowing pressure. You don't necessarily even need RTA to do this. And the resolution tends to be easy and low risk. So we call this kind of the low-hanging fruit. I would say the vast majority of production optimization opportunities exist in the wellbore. I think most people would agree with that. And these can be everything from mechanical blockages, especially in the unconventional world with multi-fract horizontal wells. You have lots of opportunity to have jewelry and gunk and stuff blocking the pathway inside the wellbore. This can be everything from mechanical blockage, unmilled ball seats, parted casing, prop and bridge. In my time at NCS, we saw tons of this sort of stuff. On the other side of it, you can also have production-induced problems such as liquid loading, as we talked about already. So these two categories make up a lot of the productivity loss that we see in wellbores, and it can be significant. So diagnosing these wellbore problems can also be done, and RTA can really help with doing that. And I'll show you a couple of examples of that. And the risk as we start to move downhole becomes a little bit more, mostly because it costs more money to go into the well. You're shutting down production operations to go and mitigate these wellbore problems, do these interventions or treatments. And then when we get into the completion and reservoir, we get into sort of the real big problems. Usually induced by fracture treatments, so things like frac face skin, low frac connectivity fines migration. Some of these things are not easily resolvable, but they are, in many cases, easy to identify. Using RTA, it's typically fairly straightforward to separate these three and at least pinpoint where the problem is. And so the difficulty and risk goes up as we move into that reservoir. So this is not an exhaustive list of issues and symptoms, but it does kind of capture the whole scope, I think, of what we would tend to see in a production scenario, especially in an unconventional type field or application. And so I'm going to show you 3 examples, one of the surface, one of the wellbore, one of the completion. In fact, the completion reservoir one is the very first example that we saw, so we'll kind of tie the loose end up at the end. This one, I've had this example for many years. I love it. It's probably the best example of a gas well being backed out of a pipeline that I've seen anywhere. This is a production engineer's dream, in the sense that, you know, with very little effort and investment, you can have a huge increase in production. So this would come across, or where you would see this is a gas well producing, for example, in a gathering system where it's being essentially backed out, a high deliverability well producing to a high pipeline pressure. And you can see this pressure is ramping up significantly. We have a great match of the data, which tells us that the problem is not in the reservoir. The problem is simply at the surface. We have a low production rate because we have a high pressure and therefore low drawdown. If we keep this well producing under its current conditions, it's only going to do 3 BCF. If we remove that back pressure restriction, we can ramp that up to 18 BCF. That's a very extreme example, but it is, you know, that was a real case that I saw probably 20 years ago. And that's the ultimate sort of low-hanging fruit, I think, for a production engineer. This one is a wellbore example. So in this case, we have a well where a rod pump was installed, and you can see we have about 500 barrels per day of oil production prior to this intervention. So the rod pump was installed, we get a spike in rate, but then the rate comes back down fairly quickly. The bottom hole flowing pressure drops from about 2,600 to 875. And we reach a peak of about 1,000 barrels per day. So the question from looking at this would be, okay, what sort of grade do we get on our artificial lift assistance here, right? Is this successful? You know, did this work? Did it not work? I'm going to say we need 2 things to answer that question. Number one is we really need to marry it with a reservoir model to see whether the reservoir engineering component makes sense. And number 2, to really resolve this, we need to know what that, we need to have confidence in our bottom hole flowing pressure, which in this case, unfortunately, we don't. This is our reservoir model. The reservoir model shows that, you know, what we observe in terms of the rate uplift here is not consistent with the inflow pressure response. The model says that the well should have been able to create that uplift with much less of a drawdown. So this leaves a question. Is the pump actually operating at 1,000 PSI, or is there a head sitting on top of the pump and we have a simple restriction in the wellbore? So the question is the restriction in the wellbore, or is the restriction in the reservoir? And we can't necessarily answer that unless we go down there and measure that pressure. If the pump is designed to operate at 1,000 pounds and the pump is operating at 1,000 pounds, then we have a more severe problem, and we have a problem of pressure loss in the reservoir itself. So you know, this is an incomplete problem, but it's something very typical of what we would see in the field, which would lead us to, okay, now we got to go and test and actually figure out what's going on here. So again, we can do a side-by-side comparison. This is the component of the analysis where we see whether it's worth our time to go and solve this problem. Is it worth your time to get 15% more EUR? I think in most cases the answer to that would be yes, but really it comes down to cost, right? If it's going to cost you X number of dollars to go in and test and measure that pressure, or go in and change out the pump if you've assessed it, that being the issue, that's really a question of economics, and it depends on the play, it depends on the product price, it depends on economics. That has to be brought into the fold. But this gives you the tools to really make those assessments. Last but not least, we have this was our original sort of sick well that we talked about right at the beginning. What this actually is a high pressure, high temperature Eagleford example. And I just showed you the production rate at the beginning, but I didn't show you the choke settings. Here you can see the choke settings. The well comes on with an 8/64 choke at 2.5 million cubic feet per day. And like many of these wells, what tends to happen is we open up the choke slowly to try and get coax out better production. But of course, with these wells being high pressure, high temperature, you don't want to do it too fast because there's this concept of gutting the well and having choke or drawdown induced productivity loss, which is very common in the Eagle Ford. So we see these two, essentially we have two sort of separate operational flow regimes, if you want to call it that, happening here. And then you've already seen this plot, I showed it earlier. This tells us that two things are happening. Number one, the A square root K, which is sort of our linear flow parameter. That's our transient linear productivity index, if you want to call it that. And when the well comes on stream, the value of that number doesn't really matter. What matters is how it changes with the two different chokes, excuse me, two different choke settings. So on the initial condition with the 864th choke, we have 18,000 roughly, and then that drops down to about 13,000. That's a 40% decrease in, and now that we don't know where the decrease happens. Does it happen in fracture area, connected fracture area, or does it happen in the permeability? But one way to think about this is an unpropped frac under high pressure conditions starting to collapse and losing fracture area. That's a well accepted paradigm for the Eagle Ford, for example, where we have very high stress dependency on permeability. The other thing that's going on here is you get a increase, the data moves from down to up, which tells us that we have more skin damage. And you're going to hear much more about that in the next webinar next week, where there'll be more examples that show how assessing that intercept and that skin damage can have a huge impact on production, and show how we can sort of high grade opportunities for improving productivity by looking for those opportunities.
Hey Dave, I'm going to give you about a 5-minute warning.
Sure, I'll come in under time for probably the first time in my life. So we're pretty much done. Those are the examples, just to sort of wrap up with some conclusions here. Again, if I haven't been a broken record about it enough, I'll say it one more time. Pressure data is critical. You can't do this with just looking at production rates. I find the industry is getting better at this now, especially with the fact that we have access to pressure data on operated wells. Typically on our desktop, we can see them pretty clearly. That never used to be the case when I started my career in RTA. It used to be much more difficult to get your hands on pressure data, flowing pressure data anyways. Our next sort of obstacle in the industry is to get from flowing pressure to bottom hole pressure. In the way the market is now, it's maybe not moving in that direction because that's more, that's just more expensive data to collect. But the value of bottom hole pressure data is absolutely worth the spend, in my opinion. You can get much more confidence out of your analysis if you have access to that bottom hole data. Understand the impact of operating conditions on the health of your reservoir. This is critical for your high pressure, high temperature plays. If you are operating in the Eagle Ford, in the Permian, like lots of regions in the Permian that are high pressure, high temperature, in the Haynesville, dry gas. And in Canada, some areas of the Montney, the Duvernay, there's a ton of these sorts of plays. The effects of productivity loss because of what's going on in the reservoir are going to be critical. You have to tie those two things together. There's no substitute for direct measurement. Having access to an initial pressure is critical. I didn't really talk about that during the talk, but James, I think, made that clear with his presentation. You can't generate an IPR curve if you don't know what your, and it's not necessarily your reservoir pressure, it's your effective pressure within the region of depletion that you're looking at. And taking these periodic measurements of bottom hole pressures become really important. So the triage concept, which is why I asked the question at the beginning, I think that's a concept that a lot of people use, and it makes sense. It's like, I've got all these wells to look at, especially in these market conditions. Maybe I don't have time to visit them all and pay attention to all of them, so I'm going to use a triage system. I'm going to try and high grade those wells that need attention the most and resolve the issues that are going to give me the biggest bang for my buck. And in general, the further you look into the subsurface, the more difficult and more risky it is to resolve those issues. So it might be worth doing an intervention if the reward is high enough, but generally speaking, it's going to be better to tackle those surface and wellbore problems first, and then move down into the reservoir later on if you can. That concludes my presentation. Thank you very much, and I'm happy to answer any questions now.
Thanks a lot, Dave. We have so many questions, and they're all really, really good questions. We're going to extend this by about 10 minutes past what we were planning to. I know all of our presenters, panelists may not be able to hang on, but if you can, great. So the other thing I'll mention is we will be answering all questions in a spreadsheet and sending them out to everyone. So if for some reason we don't have time to answer your question live here, we will be answering it personally to you after, okay? So again, anyone on the panel can answer this. The first one is, what is your opinion on proper choke management over the life of a well from the initial opening in a liquid dominated reservoir versus gas, both with low permeability? Do you think investors fail to understand the concept of increasing CUME, BOE, and EUR in our current low cost environment?
I'm sure Brian's got probably a good response to this. Maybe I'll just start and give my 2 cents to this. From a sort of investment and capital perspective, I think there's a lot of misunderstanding about this. We've seen it firsthand, especially, you know, what I would call the previous paradigm for oil and gas companies operating, which is like grow production at all cost, which isn't necessarily the best way to get net present value out of your asset, as we've found, and you get these price collapses that generally happen. And now, you know, investment is sort of running for the hills in many aspects. So what's the lesson here? Well, simply, you know, maximizing, for example, 90-day or 180-day CUME is not necessarily the best solution, right? You have to look at the long term. You have to look at this is the way I think of it anyways. And especially I think production engineers have to look at it this way also. You're looking at the asset as a cash flow generating system, right? And it's not just how much can I get out of that at the beginning. You have to be looking at it all the way through. And these choke management strategies are really, if you're doing it successfully, they should be aligned with that. So we've seen this so much in the Eagle Ford and places like the Eagle Ford, Haynesville, Delaware Wolfcamp. If you gut the well too quickly, you get these really, really steep declines, which, you know, for investors, very often you see this, what looks like a great return on investment, great return on capital investment. And it actually might be for the first, you know, 2 or 3 years, but then there's this expectation that the well will keep performing that way, and that doesn't happen. So you have to, you know, there's this endless cycle of more capital investment to keep replacing that production. And that happens at a rate of return that has been shown historically to not meet investors' needs. So I think a new paradigm, I'm going far beyond the scope and kind of standing on my soapbox here, but I think the paradigm has to really go beyond that and really try and manage the system as a, you know, net present value of the asset, manage the cash flow through its whole life cycle. What are your thoughts, Brian?
Yeah, I think I'll probably just parrot what you said, but to answer the second question first, I do think that investors fail to understand the concept of generally long-term value and waiting for those longer-term returns. They're not typically operators, and really to have an understanding of how long you want to keep your investment and keep kind of seeing those smaller returns. It takes a very patient person. And as we've seen with supply and demand changes or global pandemics, commodity prices can fall out quickly. And so I think people, especially now, are more interested in cash flow. And obviously that ripple effects through the industry and operators, and you kind of have to change strategy on what are you prioritizing individually within a company. Is it cash flow to be able to fund additional drilling programs, or is it something more long-term? If you have enough cash on hand to kind of survive it, you can keep having that long-term view. So I would say that the investors probably don't understand it, and they probably want their return as quickly as possible so they can invest in other opportunities. And then proper choke management, I think it's most of these pressure-dependent plays, it's very well understood that some form of choke management is needed and optimization of that to deliver those long-term net present values can sometimes be difficult to ascertain when you're talking about, forecasting 10, 20, 30-year EURs and some of the uncertainties associated with the reservoir performance and well performance over those kinds of time periods. Are you even going to be able to produce the well in 5 years from now? What are the commodity prices going to look like? So there's a lot of competing factors on the operators to say, maybe the long-term best economic decision for this well would be the most conservative choke strategy, but due to whatever the current commodity environment is, we can't afford to do what's best and ideal for us. So we need to make a balanced decision on that approach and generate more cash up front and gut it a little bit harder in order to, meet whatever our current strategy is. So it's really a trade-off.
One more thing to add, just from a technical perspective, because I think the question was, as you correctly said, Brian, was focused around the liquids. If you have whatever choke management strategy you have, if you're comparing that for dry gas as opposed to liquids rich, it becomes even that much more important, especially if you're interested in maximizing liquids recovery, because you're always going to be dealing with this saturation pressure, whether it's a rich gas condensate system or volatile or black oil system, where your liquids recovery, if you open up the choke too quickly, is going to be lost forever, right? Liquids recovery potential. So you want to, from a reservoir perspective, you want to leave as much of that, for example, in a gas condensate system, you want to leave as much of that condensate, or recover as much of that condensate at high pressure as you can. So if you start to draw down below your dew point too quickly, unless you have some sort of gas reinjection program in the wings coming in later on, you're going to lose that liquid recovery potential forever. And that's layered in on top of all the stress dependent problems that happen. So a choke management strategy in a liquids rich environment becomes doubly important for preserving that liquids recovery. I think both the condensate system and if it's an oil system.
Great. We've got a few minutes left. I just want to remind everyone in the audience, we will be getting all the answers to all questions out to you after the meeting. So I'm going to answer this next question. And the question is, with all of these advances, are we close to being able to having an integrated production model, reservoir plus well plus surface hydraulics? So I'm pretty happy to say there is a technology available for this now. It's called Harmony and Piper, and it does a fully integrated asset modeling, including transient flow in the reservoir. The only limitation, it doesn't consider multi-phase effects in the reservoir, so it's relying on analytical models. So I'm saying, what I say is, we're partway there. We're trying to get further. That's the short answer. Anyone want to chime in before I ask the final question?
No, I think you hit it on the head, but I like that the question came up, as I'm sure everybody would agree that looking at the full system all the time as things are changing, an operational change on this well could affect the bottom hole pressures on that well. These things are important, and having the capabilities to monitor all that through the life of an entire field or a larger area is very important.
Awesome. I'm selfishly going to share my screen for a second, because I came across a particular
I'm not
slide.
surprised.
I know. I came across a particular slide the other day that I think really, really represents this whole topic. I'm gonna give everyone a quick second to look at it, but I call this slide the pressure loss game, because I really like it, because it talks about where we're starting at from, the pressure in the reservoir, how we're losing that pressure through the permeability or multi-phase effects, and then the pressure loss across the completion, and then of course into the wellbore, up to the wellhead, the choke, the separator, and then through the pipelines, of course. So this, imagine if we had something like this for every single well. I think we would be able to see the opportunities that we have to maximize our production. So I love this illustration.
It's a great way to visualize it. It shows you how important pressures are to the system. It's not really, production optimization is not about production rates as much as it is about the opportunities are to reduce pressure losses.
Exactly.
And the improvement in rates come as a result of that, not the other way around.
Awesome. Okay, well, the very last question I'll ask here is, Sorry, just gotta pull it up. Okay, do you have any low-cost techniques to estimate bottom hole pressures for rod pump wells beside fluid levels? It says dynamometer cards, pros and cons, any best tools to capture this data?
That's got to be a Brian question.
Yeah, that is definitely a Brian wheelhouse question.
Yeah, I would say that fluid level shot is probably going to be the cheapest option you have for trying to assess the bottom hole flowing pressure in a rod pump well. There's not much more you can do because you don't have to enter the well bore. You just have to hook something up at surface and go from there. So I don't think there's much more than that, other than, of course, using some sort of a correlation to estimate what that bottom hole pressure might be at the pump, and then maybe applying, if you find it to be a little bit inaccurate, apply an additional pressure loss across the pump to estimate the intake pressure. But I think the fluid level is probably one of the cheapest options.
I had a conversation about this years ago where someone mentioned being able to use the torque or the tension on the rods to get an estimate of what the suction pressure of the pump might be. But then I brought that up to Louis and he looked at me and said hogwash. So I don't know if there's something there or not, but there might be some documentation out there worth looking at to see if there might be something there. Just as far as a cheap option, using information you're already collecting anyway might be, but how useful it might be, let us know.
Awesome. Dylan, do you want to wrap us up?
So thank you everyone, first of all, for joining this webinar. So we will, as Graham says, be getting all these unanswered questions to you in a spreadsheet format. It may take us a little time to do that, but please bear with us. We'll be asking the presenters on whether they are able to share their slides, as I've indicated. So we'll be able to share that information with you, hopefully within the next few days. If you have any other questions, feel free to obviously contact us. I encourage you to stick with us for the second webinar, which is happening next Friday. So part 2 of this webinar series. You can go to sagawisdom.com to register for that.